Well, let's pick off where Waffman wasn't quite the order that I planned to do. Yeah.
I work at the help desk and I have administrative privileges on Internet. I could probably fix it.
Well, I think it's doing it now.
Oh.
I tend to type the domain name before the thing goes. So if it doesn't, then I'll let you give your little magic try. When we did the Schrödinger equation when we started out, we did a lot of things where we built in de Broglie, we built in the Einstein photon equation, we built in classical physics was built into energy conservation, and we ensured waves. However, what we didn't do was ensure that the waves had any physical meaning. Just because something's a wave doesn't mean that it implies that it means anything physical, that it actually describes, say, an electron or a photon or what have you. It could be a wave that's just purely a wave function that has no thing to do with reality whatsoever. So if we're going to make sure that the waves have physical meaning, then we have to ask ourselves what the wave function is supposed to tell us. Now, it tells us lots of different things in general, but one of the things that it's got to connect to is this idea of probability. We saw that in that film a little bit ago that we did, I don't know, a couple days ago or such, but it was kind of real quick and we went over it. I want to go back to that and in particular look at this concept that Born has between probability and the wave function and how they are related. They're not related directly to the wave function. They're related to the square of the wave function. And so the wave function has to have certain additional properties besides the fact it just comes out of the Schrödinger equation. Or it can't be anything physical. It can't have any meaning. So I want to go back and look at that part of the film, if I can. Maybe it'll let me just a second here. And see what the physical significance forces upon us. Come on. Mechanical universe. We're in the particle and waves video if you want to go and look at it yourself. So let's go back and look at this.
It was the heart and soul of Erwin Schrödinger's wave mechanics. Light passing through two slits causes an obvious wave interference, which clearly reveals itself as a pattern of light and dark stripes. There is no question about light being a wave. Only waves behave this way. So the question is, how can light be particles and still interfere like waves? If light is made of photon particles, individual little things which can't arrive as a spread out pattern, then each particle has to hit the screen individually. A single spot of light here, for example, another photon there. It's impossible to predict precisely where any spot will appear, but it is possible to see that more photons land in some places than others. In fact, there's a higher probability that more photons will land in certain regions. And eventually, because of those probabilities, the result will be a definite wave-like diffraction pattern of particles. This was the explanation proposed by Max Born. Photons might be particles, he said, but the patterns they make are ruled by probabilities that interfere as waves. And one of Born's colleagues.
Okay, so that's really kind of the thing I wanted to get out of that. It's this idea that the wave function in some way is connected to probability. All right? But it's not the wave itself, because if you had a wave, let's say it's a sine or cosine, then the sine function could have negative values. It have negative probabilities. What it is the square of the wave function. And since the wave function can be complex, one has to ask what we mean by squared. What we mean is, in a complex plane, it's the length of the arrow. How you find that is that you take the wave function and you multiply it by its complex conjugate. So if you have something like e to the I theta, you multiply by its conjugate e to the minus I theta, and that eliminates and you get just a real number. And that real number is the probability density. That's the distribution function that we talked about back in chapter 2. That's the thing that you have to use to calculate the average. That's the thing you have to use to calculate the standard deviation. That's what you have to use to calculate position. Everything about the thing involves you getting the probability distribution. But to get it, you have to solve for the wave function. And to solve the wave function, you got to solve the Schrodinger equation. So, last time we talked about solving the Schrodinger equation. We already talked about what to do if you have a distribution function like a binomial or Gaussian. What's changed now is you have to do quantum mechanics to find the distribution function. And then you have to be able to do everything back from chapter 2 about probabilities and distributions. They weren't going away. I told you the reason we covered them is they were coming back. I was just covering the part about what you did once you got the wave function. What you do is you have to do this probability stuff. Now, if you look at what the function has to be probability, it has to have these properties. Otherwise, it doesn't make any physical sense. For one thing, the wave function has to be continuous. Because if you square it and it's discontinuous at a point, then that would say that at a single point, there would be like two different probabilities. So what's your probability to be at that point? Oh, well, I'm either 40% or 20%. Doesn't make sense. So the wave function, much like the position vector, can't just have discontinuous. It's got to be continuous throughout. So if you have a discontinuous function, there's a problem. Furthermore, the wave function's got to be finite. Why? Because if you're going to integrate the probability distribution, then you got to be able to normalize it. The integral over all space has to be 1. If this thing goes to infinity, the integral may not go to 1. It may go to infinity. So you can't have infinite probability. So it must stay finite. Can't go to infinity. The wave function must be single value. This is kind of back to that thing with continuous. You can only have one value. We're going to deal with things like rotation. So if you think about if you had a particular rotation, there being one value of probability, if you rotate that thing around 2 pi, where are you at?
Where you started?
Huh?
Where you started.
Where you started, you better have the same probability distribution again. So if the thing can be rotated 2 pi and it doesn't get you the same answer, then you got a problem because you got two probabilities at the same point. We're going to use that as condition. In fact, that's where some of the quantum states come from. They're spherical problems. And you can rotate the angle t by 2 pi. In fact, you can rotate by 2 pi, 4 pi, 6 pi, integer numbers. Why they turn out to be integer rotations. Plus and minus. Why plus and minus? Because you can go this way. You can go the other way. That's where we'll set the so-called magnetic quantum numbers of quantum physics. In fact, they have to be single value. If you don't have infinite forces, which amount to infinite potential energies, then you should not expect the change in the probabilities to be anything but finite and smooth. Put another way, if you change the derivative, it should be continuous as well. Now, that won't happen if you have an infinite force. Just stop. But where in the world do you ever really have an infinite force? Nowhere. So really, all real-world problems have this. Do all problems in textbooks and homework have that? No. Why not? Because the finite well, as you'll find out in the later part of the module 10, is a lot harder to solve mathematically than the infinite well. The infinite, well, math is easy. So a lot of times you have a particle that has maybe, say, 1/10 of an electron volt of energy, and the well is 30 electron volts of energy. So for all intents and purposes, it's like you trying to buy Bill Gates' house. In theory, it's possible. But it's sure as hell highly unlikely. All right? So you can treat it as the infinite square well and get about the approximate answer to a semiconductor or electronic device, even though you didn't do the problem the true full way. It would be harder. And so we take advantage of that. If we can do something by hand and make the math simpler, then we're going to do that, rather than try to work the problem exactly and make the math really, really hard. And last and most important is, when you take the wave function times its conjugate, you get the probability density, and if you integrate all probability over all space, you always have to get 1. 100% the particle will rise somewhere. Okay, you've got to normalize the probability distribution. These 5 things are required of any quantum system. So, it's got to fit the Schrödinger equation, but our solution also has to fit these, and if it doesn't, we've got to throw it away. With that being said, let's try the particle in a box and see what we can do with the particle in a box. The simplest problem besides a straight, plain wave, free particle that's done, we've already done, and which is done first in your book. So the first problem is plain wave, we've already done that. And the second one is to try to do something like this. You got huge forces over here. Take a lot of energy to get over there. Giant fence. And you got a particle in here. And inside of here, there's no potential, which basically means it's free, like this room. And it's able to go back and forth in the room. But it doesn't ever have enough energy to get out, so it's trapped. So what things are trapped? Proton in the nucleus, neutron in the nucleus, electron in a crystal, atom in a crystal, electron in an atom. Lots of things trapped. So this is like the simplest model to represent something that's bound. What's not bound? A particle that goes in a straight line at constant speed away from here. A bomb. By the way, things that go boom are not called stable. They're unstable. They don't tend to be around. So the first type of small thing, an atom or something, that you wanted to describe as probably bound, you're going to try to use this model probably. So my U function is really simple. It's 0 in here, and it's infinity if you're over here in the black regions. Now, I sent you some stuff from the book by Roth. It is known in nuclear physics and elsewhere that the solution to the lowest energy state turns out to be even functions. This is one of the things we find from nature. And the reason they're even is they like the right-hand side, the positive x, just as much as they like the negative x. Now, we don't usually call them even functions in quantum physics. We say they have even parity. Basically means the thing. And there's a parity operator that you apply the wave function, it'll get you this information back. I didn't do that. If you looked at mine, I didn't put the axis in the middle. And the reason I didn't do that is if I put the axis in the middle, I get cosines for some of the functions, sines for some of the other functions. The math gets more complicated. And the only thing I gain out of this is that, well, it kind of makes sense that nature would be symmetric. Oh, phooey, let's forget that. Let's worry about getting energy levels and being able to solve quantum and make the math as simple as possible. It is much simpler if you make the math at your level, if you put the origin here. So you want to look at the more advanced treatment, look at Roth. But I've decided to make all of my particle boxes have their axes here, not in the middle. And I understand there's some experimental evidence, if I apply this to nuclear physics, why I wouldn't want to do that. But this isn't a nuclear physics class. We'll talk about that if you get there, okay, if you decide to take that. So, if that takes an infinite amount of energy, how often does the particle reside here?
0 times.
Huh?
Never.
Never. So probability is 0, so guess what the wave function is?
0.
0. 0 times 0 is generally known as 0. And what do you think about over here? Same, so it's 0. So that's easy. I got to solve all the space. That's never. That's never. And the only thing I got to solve is in here. So I've already worked 2/3 of the problem, and I haven't done anything except call it off my head. So that makes this pretty nice. I do have to solve this problem, but in here, there is no u. So the u falls out of my equation right off the bat. That also makes life really nice, because the only thing I have is a constant e. I don't have a u with any function of x. And inside here, if you have constant values of u, in this case 0, then you're going to have constant potential energy, you have constant kinetic energy, therefore you have constant momentum, therefore you have constant wave number, therefore the solution should be, what is a fixed wavelength? What type of functions?
Sine, cosine.
Sines and cosines. So that should be the answer. And that's what the math shows. And I worked that out for you in detail in the notes. So nice things. Break it into 3 parts. Part 1, Part 2, and Part 3. 3 different values of u. But this and this are already solved. The wave function 0. The only thing you got to solve is that. So if I write Schrodinger's equation, I have the second derivative of the wave function. Notice the subscripts too. Why? Because I'm talking about the wave function in this region. Is equal to minus k squared times the wave function. That's just the time-independent Schrodinger equation.
Dr. Marwin, could you...
Oh, I'm sorry. Didn't see I was off the page. Thank you. So what I'm saying is, see these little subscripts? That's there because the only part I'm solving is in here. A lot of times you'll have to solve this side, this side, this side. You need to remember which one you're doing. They're not going to be the same functions. Now I'm going to find k squared. K squared, I remind you, from last class, is 2me minus u of x over h bar squared. That's just the kinetic energy, which is p squared over 2m. If the 2m cancels, that makes it p squared. P squared is h bar squared k squared, but I'm dividing by h bar, so I have the wave number squared. And if you like, you could say this is this. There's your wave number. It's your wave function, or wavelength, I mean. But u is what? For region 2? 0. So the wave number is 2 times the mass times the energy over h bar squared. So we're looking for the states of constant energy. The mass is constant. H bar is constant. The energy is constant. So k squared is constant. Also, the energy is going to be just kinetic. P squared over 2m. So the kinetic energy is positive. So that means positive, 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 positive. Means it's positive. So I can tell you it's greater than 0. So I have an equation here. That second derivative is minus the constant squared that's greater than 0 times p. Now in the last set of notes, I said to know the solution for this equation, if k squared was a negative constant, k squared was 0, and if k squared was a positive constant. It's a positive constant, it turns out, it's sines and cosines. Or it's complex exponentials, it's your choice. If a problem is bound, that is, it's got some limits, sines and cosines will make the math easier. You don't have to do it, it just makes the math easier. If it's free, so it goes up to infinity, you probably don't want to be trying to figure out what the cosine of infinity is. A times the cosine of infinity plus b times the sine of infinity equal 0. Solve. that is probably not one of the ones you want to do, okay? So in that case, you probably don't want to deal with this. You want to deal with plane waves. Why plane waves? Because in plane waves, one of the waves is going in the positive x, and one of the waves is going in the negative x. So you could think of one of them as like being a particle coming in, and one of them bouncing and coming back. So you'll find that useful in barrier problems. When you're throwing electrons, and some of the electrons get transmitted, and some of the electrons get reflected. We talk about transmission and reflection coefficients. So anytime you get this equation, and it's bound, you probably want to use the sines and cosines to make it math. And anytime it's not bound, you probably want to think in mathematics in whatever class you're in that you want to do exponentials. Hopefully you'll master this, because from now on, junior and senior year, we will expect you to know this equation off your head. We will not waste time stopping and talking about it anymore. You've had it for 2 years, you should be an expert in it. We will just use it in homework, and it will be thrown at you, and nobody will talk about it. And you can either solve it or you can't. You just don't get your homework right. But you will have a lot of problems. Know it. It's highly useful. So, bound, we chose cosines and sines. So, it could be a sine function. It could be a cosine function. And we know this. The k in there is the square root of 2me over h bar. So, if you give me the energy, I can find the k. But I don't know the energy. I want to find the energy. So what I want to do is I want to solve this. And from this, find the k. And then with the k, I want to go in here and use this equation to find the energy levels. That's how I'm going to do it. So how am I going to find the k? I'm going to look at the boundary conditions. A differential equation has infinite number of solutions without boundaries. It's the boundary conditions that quantize things. So it's the boundary conditions that are going to set the k. It's the boundary conditions that set the k that set the energy. So what we need to do is take this general solution to the equation. We need to look at what happens to the function when it gets to the boundary at 0 and when it gets to the boundary at L. Now, remember our requirement. When it gets here, the wave function must be continuous. So over here, I got sines and cosines. But when it gets here, what's the value? 0. So that means the function for these sines and cosines has to equal 0 when x is 0. And you got sines and cosines over here. But when it gets there at x equal L, what's the value got to be? 0. If it's not, then the fact that you cut this altered the problem, and you don't have a continuous wave function, and you don't have a proper solution for quantum mechanics. The wave function has to be continuous. I know the answer in this. I know the answer over here. Therefore, I know the answer at the boundary. And you have to make sure it matches. So you got some advantage by cutting this thing up, because I didn't make you solve a rectangular differential equation, which you have no way to solve. But on the other hand, if you haven't mastered your math properly, then you're about to get creamed, because you have to be able to match boundary conditions. Now, sometimes a problem might be better to just attack straight on, but almost never. 99 out of 100 times in a physics problem or an engineering problem, when you have a differential equation and you have boundaries, you break the problem into parts, and then you take the individual parts and you stitch them back together. Because that's the easiest. Why? Because you probably don't even know how to attack the differential equation without it. Fourier won't work. Laplace probably won't work. A calculator, you might as well put that thing in the trash can because it's totally worthless. All right? For all your advanced course, you just take your calculator and put it away because it's basically worthless. You've had your time with the calculator. From now on, I hope you mastered all that calculus because you're going to need it for the rest of your life. Okay? There aren't going to be numbers, and any calculator is going to help you. There'll be infinities in the problem that cause computer programs to crash. I mean, infinity's in problem because your calculator crashed. That's why we sent you to calculus class. So you're going to want to be able to stitch that thing to those boundaries. Now when I stitch those at the boundaries, that boundary and this boundary, this one's the easiest one because when I put x equals 0 in, what happens to the sine function? What's the sine of 0?
0.
So that goes away. So that means that b times the cosine of 0, what's the cosine of 0?
1.
1. So b is equal to phi, but phi is 0. So therefore b is 0. And that eliminates that. Although that was a perfectly good solution to the Schrodinger equation, it doesn't match the boundary condition for this problem. I still have A. We'll get to A. A is going to be solved by normalizing the probability. But I want to look at what happens when you put in L. So if I put in L, on our second boundary condition, I get this. Phi2 of L, which is 0, is A sine of KL. And that has to be true. Now, one way that could be true is A is 0, right? But if A is 0, going back to my wave function here, if that's already 0 and now A is 0, then what's phi? That's gone. If you make A 0, what's going to be phi then? 0. And where's it 0? Everywhere. So it's 0 everywhere. What's the total probability of finding the particle? 0. The particle don't exist. If you're told find the wave function for an electron, and you say there are no electrons, that will be a wrong answer. All right? So A cannot be 0. Because if A is 0, you're saying the problem don't exist. Well, then if A is not 0, so that can't be 0, then that means this must be 0. The only way that can happen is if these signs are 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi, 10 pi, 11 pi, 12 pi, and so forth. 0 is not a good choice because if you put in 0 for k, you would get phi is A sine of 0 times k. 0 times x. What's 0 times x? Come on, people.
0.
I hope you're going to do more weight this. You're going to get creamed on my test. So you get A sine of 0. Sine of 0 is 0, and you have no electron again. So you may not allow n to be a 0. It has to be a positive integer. And then solve for k. And now that I know the wave number, I know p. And because I know the energy is p squared over 2m, I now know the energy. So those are the energy levels of the particle in the box, and I will expect you to be able to derive them from first principles at any time. I'll also expect you to know it off your head, and you will be asked a lot of questions on it. It looks a lot like the equations that we had before for the Bohr atom, except the energy here has the n squared on top, yes. It doesn't have the n squared on bottom. So the particle in the box, with the Bohr atom, we had things like this. There's an atom here, and there's a big gap, and then there were smaller gaps. And this was like E1, E1 over 4, E1 over 9, and so forth. With the particle in the box, you have an E1. The next one is 4E1. The next one is 9E1. So they don't get closer together, get farther away. So you get a very different set of energy levels. And consequently, if I was to look at the lines that were emitted, the lines would look different. So by looking at the lines, I can then work backwards and figure out whether this is the way the force looks, or whether that, the Coulombic force, is the way the lines look. And that gives me how I look inside the atom and tell the model. But I have to be able to work backwards. The particle in a box is the main driving force of electrical engineers. You can't handle it. You can't be an electrical engineer or engineering physics major. It is what does semiconductors. All right? It is the simplest of all models that describes electronic transitions. Now, they get a lot more complicated. They're going to get a lot more complicated. Just one thing, they're not infinite. They get to be finite. We can talk about Bethe Bloch functions and solid-state physics and such, which are much more complicated math. But this is the simplest one that can be done. And that's why it's such an important one for us. All right. So, big things, key points. Energy levels in a particle in a box go as m squared E1. That's n squared. And if you looked at this guy closely, it's hc squared. Do you remember my 1240 eV nanometers? Times E naught, where that's the rest energy. And that's L squared, the length of the box. And the wave function that goes with that so far is this. So the states, starting at 1, 2, 3, 4, 5, 6, have that for the wave function. And the square of that is the probability function. And each wave function is associated in energy. They're energy states. They're not bars anymore on a diagram, like in the Bohr model. That'd be the energy of the bar, the little levels I draw. This is what the level is. More complicated. The function, it contains more information. It contains everything you can know about this. I can apply the momentum operator and get the momentum from this. I can apply any other operator and get any other information. I can find the position of the electron with this, the some probability. I can find the uncertainty of the electron with this. It contains more information than just the straight lines across in the energy diagrams. Now, this A has to be normalized. Because right now, if I square this, I don't have a probability distribution. I have an unnormalized probability distribution. So one thing else I need to do is I need to do this. 1 times the integral from minus infinity to infinity of psi star psi dx has to equal 1. Well, that becomes a squared from 0 to L sine squared. This was 0 from minus infinity to 0, so that part of the integral has no area under it. And it was 0 outside of L, so that side of the integral has no area in it. And in between 0 and L, this function I squared. There's the a squared, and I have a sine squared. I got to be able to do that integral. Probably can do that integral. Should be able to do that integral. I want to look at that integral instead of doing it the hard way, because you should be thinking about how to do integrals besides just beat your head against them. First of all, I don't like the fact that this and that are not the same. So let us define something called squiggy. And squiggy is going to be defined as m pi x over L. Then the derivative of squiggy will be n pi over L dx. Now I'm going to rewrite that. How about L over n pi squared? So I can replace that with squiggy, and I can replace dx with L over n pi d squiggy. So I'll do that. 1 is equal to, and I have a squared, and I have L over n pi integral sine squared of squiggy d squiggy. And it goes from 0, when I put in x, then when I put in L, what happens? Where does it go? What's the top limit? In pi. So let's draw that. I didn't quite draw them right. They should be the same height. That would be the sine. And if I drew the sine squared, I didn't draw that thing. Let me get rid of this guy here because I don't want him. I'm just using him to. So you should get a bunch of humps like that. And the first one, that goes over till it gets to 0, which is, where does it get to 0? Pi. This one gets to 0 at 2 pi. This gets to 0 at 3 pi. This gets to 0 at 4 pi, and so on and so forth. Yeah. In pi. So there's one hump to 4 pi. There's 2 humps to 2 pi. Guess how many humps there are to n pi? Yeah, there'd be n humps to n pi. Now, what's the area of the rectangle?
N pi sine.
N pi times the height of sine squared is 1, so the total area is n pi. Now, but we don't want the rectangle, right? We only want these guys. So let's just look at a couple of them. Let's say we went this far. I got 2 humps, right? I'm missing a hump. I'm missing half a hump right to here. And I'm missing half a hump. So I got 2 humps, and how many humps am I missing? 2. So what fraction of the area did I cover? Now, if you go to 3, I got 1, 2, 3 humps, and I'm missing 1 hump, 2 hump, half a hump, and half a hump. So I'm missing how many? 3. So I always get half the area. What's the total area of the rectangle? In pi. What's half of it? N pi over 2. So this thing here is n pi over 2. And I don't think I did any advanced calculus or anything to do that. So a squared L over n pi times n pi over 2. What happens to n pi? So a squared times L over 2 is 1. A squared is 2 over L. So A is the square root of 2 over L. And notice there's no n in there, which means that no matter which wave function you're on, the first, the second, the third, the fourth, the 10th state, they have the same peak. Not all functions do that, but some do. So the only thing that I would change is that I would replace that with this, 2 over L. That's the final result of the particle in a box. Everything you need to know to work any problem is completely contained in that solution. But you need to work through the solution because harder problems will require you to do all the steps in a particle in a box, but the math will get harder. They'll have Hermite polynomials, they'll have Legendre polynomials, they have spherical Bessel functions, but you still have to be able to do all of these mathematical steps of separation yourself. So at least with sines and cosines, you have some experience. With the others, well, welcome to the fact that we don't build things just out of cubes. Sines and cosines come out of cubes. Bessel functions come out anytime you build a cylinder, which means every coaxial cable that you ever deal in electrical engineering. If you ever deal with a sphere or ball bearing, then you're going to deal with spherical harmonics. That's just the way the world is. We're not going to build everything with rectangles. Rectangles have corners. Corners cut. Therefore, they are not rarely ever used in engineering practices. If you're pumping oil, it's going to be through a cylindrical pipe. You've got Bessel functions. If you're pumping water, it's cylindrical. You're going to do Bessel functions. If you've got a coaxial cable, you're going to deal with Bessel functions. You get a lot more practice with them and in great detail with the math of them and math methods, but you're going to be using them in every course. So, first time you really get hit on them is here. Because we're no longer going to deal with one-dimensional problems pretty soon. The world is three-dimensional. The days of 1D has to go away. That's kind of why Cal 3. So, make sure you can do a one-dimensional problem because it's the simplest, and then everything else will just get harder. Okay? If you don't be able to do that one, then you're going to really not have much chance when you get to harder problems. I gave you a set of problems to try to cut your teeth in on each one of these guys, and the one for test your knowledge was a particle in an infinite well, and it said, answer the following questions for a particle in a box with infinite walls. First, write the wave function for the ground state and the first excited state. All right, ground state is the n=1 state. So that's the square root of 2 over L sine of pi x over L. 0 less than or equal to x, less than or equal to L, and 0 otherwise. The first excited state would be the n=2 state. Square root of 2 over L, but now I got the sine of 2 pi x over L. 0 less than or equal to x, less than or equal to L, 0 otherwise. So if you know the solution in the particle of the box, that problem is like that. If you don't, you get to derive it from first principles. It then asks you to draw the excited state. So first thing they can do is ask you to write it. Next thing they usually ask you to do is draw it. Okay. So what you're saying is, can I draw that? Well, let's see, it's a sine function, so it goes. That ends at L. That's at L over 2. And it's 0 otherwise. So. That's it. Let me ask you a question. Is that a periodic function? This is for engineers. This should be a simple question for an engineer. Is that a periodic function? No, it's not periodic. It doesn't repeat. Next question also should be a simple question for an engineer because they take a lot more of this than physicists. And that is, if it's not periodic, what can you say about the Fourier transform of that? You do frequency analysis. In other words, how many different waves of wavelengths are required to make a graph like that? The answer is an infinite number. So therefore, there are an infinite number of wavelengths, an infinite number of wave numbers, and therefore an infinite number of different momentums that are required to solve this. It's not just single wave in there, it has to be a wave packet. Why? It's been confined in space. It doesn't go on forever. This is the Heisenberg uncertainty principle. If you're going to be an electrical engineer and engineer physician, you should feel totally comfortable in bouncing between frequency space and regular time space, because that's what double E's do. All right? This is one of the things 225, feeling in EMPH and electronic circuits, you should become totally comfortable with. It should be able to work, but you never get another course in it. Everybody assumes you know that. Physicists don't have that course. They pick it up later. But it is one of the important things about the Fourier. When a Fourier looks at a wave that's periodic, its transform is discrete. It has a finite number of wavelengths. What that says in quantum is a finite set of momentum. But in something like this, it's aperiodic, so it'll be continuous. So when we get energy levels at the end, there's a contradiction, because this thing says there should be different wavelengths. Therefore, there should be a band of energy. And that's because we made it infinite walls. And that means this problem is not well defined. It can't represent a real physical problem. And it turns out the band will be small. So people forget, just kind of ignore it until they talk about momentum. So find a good problem book, and they'll give you problems on momentum. You'll find that they have a lot of different ones, not just one or two. And then look at energy, and they talk about it like it's a delta function. They don't seem to make up their mind, and that's because of the particle box. They also will ask you to draw the probability distribution. So now I'm looking for the wave function squared. And it says 30-sided state, so that's P4 of X, which is psi 4 star, psi 4, or sometimes called like this, absolute value squared. So this thing should have had, if it was 1, n equal 1, how many humps did it have? 1. If it was 2, it had 2. If it was 4, it will have 4 humps. That's really useful. If you know that, you can just draw it off your head. Otherwise, you can sit with the calculator and start trying to generate all this stuff. So there are 4 points in which it's a maximum probability of finding the electron. There are also 1, 2, 3, 4, 5 points where there's a minimum probability of finding the electron plus all these points outside the box. The height is the probability density at any point, 2 over L. Because I squared the square root of 2 over L. Problem number D. What's the probability of finding the particle between 0 and L over 4? Well, let's see. This was L. That was L over 2, or 2L over 4. This would have been 3L over 4, right? This would have been L over 4. Now, here's an example where you can use a graph to solve a problem, or you can spend a lot of time doing integration. The question is, what is the probability? Which means integrate from 0 to L over 4, 2 over L, sine squared, times 4 pi x over L dx. Do that interval. Find you the answer. If you do that, you'll find the same answer I'm going to find without doing so much work. You're saying, what's the area under this curve? Well, the sum of the humps has to equal what?
1.
1. What's the area under the one hump?
1.
Bingo, that's the answer. 25%. Now, you'll get that answer if you do the integral. but sometimes it isn't necessary to do an integral if all you're doing is you've got a good graph. You can do that here because these humps are all the same height. If these humps are not the same height that's in a harmonic oscillator, for the humps on the end are greater because it moves slower, then you're going to have to do the integral. Right? But for these guys, my gosh, I wouldn't want to do a bunch of work on humps because that's going to take a lot of time. It asks you to draw some energy diagrams. So there's one further, and then really far up. 1, 2, 3, 4. E1, 4E1, 9E1, and 16E1. Really, the only thing you got to find is what?
E1.
E1. E1 is going to be HC squared over what? 8E0 squared. So E1 is 1240 EV nanometers squared over 8 times 0.511 times 10 to the 6th eV times 2 nanometers squared. Again, notice how useful HC is. If you change the particle, if you make the particle more massive, the energy levels are going to get closer together. If you squeeze the box, what's going to happen? Make L smaller, what happens to E? Gets bigger. This is the inverse relation between space and energy that exists throughout. So if you squeeze the box, it's not an electron in an atom, it's a proton in the nucleus, and you just lowered the box by 5 orders of magnitude, then you just increased the energy by 10 orders of magnitude. We've left EV land, or milli-electron volt land, and just went up to mega-electron volts of energy, which is why nuclear physics power can do so much more than chemistry or gasoline, because the thing is confined in a smaller box. And you're not going to find any new product that's going to replace that, because the atom has a fixed size, and that's just the way the world is. Put your numbers in there, by the way. This 10 to the 6 kind of knocks out the 10 to the 3rd, so that's about 1 squared.